Welcome to AP Biology. I want to talk about chemical bonds today because that's what holds your atoms together in all of your molecules. So your body and the bodies of every living thing around you are made out of molecules. Molecules like sugar and maybe starch or glycogen and cellulose and chitin and various proteins and phospholipids and triglycerides. All those molecules are made out of atoms like carbon, hydrogen, oxygen, nitrogen, and all those atoms are held together with bonds. So what are the different bonds? There are ionic bonds, two different types of covalent bonds, and then we have hydrogen bonds, and then we have some weaker interactions like van der Waals interactions or hydrophobic interactions. So today's goal is to understand all those different types of bonds so that you can understand how these bigger molecules are held together and how they interact with each other and how they interact with water. It's important to look at water. It seems like sort of like this random little thing, but water is actually really important because every living thing has its basis in water, right? You've got water in your cells, water outside of your cells. So we're going to look at that. So we're going to start by looking at ionic bonds. Ionic bonds are when you have ions that are attracted. So here's sodium and chlorine. So sodium has 11 protons. And so to be neutral, it's got 11 electrons or negative ones. You can fit 2 in the first shell, 8 in the next, so that makes 10. So then you've got this extra electron right here that is not a very full valence shell, and it turns out that sodium doesn't hold its electrons very hard. Just looking at this picture, it seems like it makes sense that sodium would lose an electron because otherwise to get happy it would need to gain 7. It's just not going to do that. Look at the periodic chart. Sodium's way over here. Remember, to be electronegative, you're going to be that way and this way, right? So these are your very electronegative atoms. So sodium doesn't hold on to its electrons well. It's got 11 pluses and then it lost an electron, so now it only has 10 minuses. If you look at the balance of plus and minus, there's more pluses, so sodium ends up being a positive ion or a cation if you want. Here's chlorine, and it's got 17 pluses, 17 protons in the nucleus, 17 electrons outside. The outer shell here has 7, so it actually needs one more. And if you look over here, chlorine is actually very, very, very electronegative. So it's going to tend to pull the electron from sodium to itself, and that will give it a full valence shell, valence set, 8 electrons. So it's got 17 pluses, it steals an electron, and so now look at this, it's got one more negative than positive. So overall, the chloride ion is negative. So the ionic bond is just the attraction of a positive to a negative, a cation and an anion. Okay, so here's what an ionic compound might look like. You've got chloride and sodium and chloride ion and sodium, and they just kind of make this big nice little crystal. This is what they look like. It's a strong bond, but I want to show you now what it does in water. So let's take a look at that. So I'm going to draw out water a little bit, and I've got to define another type of bond in order to show you what sodium and chloride ions do in water. So remember that water is H2O, so it's got 2 hydrogens for every oxygen. So if I were to draw that, oxygen has 8 protons, and you can get that right from the periodic chart. There's no need to memorize that. You can fit 2 electrons in that first shell, 3, 4, 5, 6, 7, 8. Notice it is not full. It has 2 lonely electrons here. So what's it going to do? In this case, it bonds with hydrogen. Hydrogen has 1 proton, 1 electron. They're going to share here. That sharing will, in effect, give hydrogen 2 valence shell electrons. Hydrogen's going to do that here too. Same thing. And now oxygen has 1, 2, 3, 4, 5, 6, 7, 8 electrons, so it's happy too. So I might draw water like that, or I might draw it like that. Notice that it's a bent molecule. These electrons here actually take up physical space, and so the hydrogens end up getting pushed near each other. So that's water. I want to compare that to, and actually I should define this too. If you share electrons, you end up making a covalent bond. So a covalent bond is made by atoms sharing electrons. They could share them evenly or unevenly, so I want to show you that next. But a covalent bond is very strong. So I'm going to show you one like hydrogen. So that's H2. So you have a proton and an electron. That's hydrogen. And then another proton with an electron. So if you look at these two electrons, they go around both of them. This hydrogen doesn't pull any harder than that hydrogen. So this is even sharing. And that makes something called a non-polar covalent bond. This is actually also, besides having a non-polar covalent bond, it's also a non-polar molecule because there's no extra electrons on one side or the other. They pretty much just spin around both. It's a probability curve, but for our purposes, drawing them like this, I think works fine. So this is called a non-polar molecule. Now let's compare that with this bond. So remember how we said oxygen is very electronegative? The number for oxygen, there's numbers for this stuff. Let me move myself. The number here for oxygen, its electronegativity is 3.5. The electronegativity of hydrogen is 2.1. So the difference there is going to be 1.4. So this is in your packet. I think I sent home this packet, chemistry review. This is really the basic stuff that you need to know. So I think I came up with 1.4. So 1.4 lands somewhere in here. So there are nonpolar bonds, polar covalent bonds, and then ionic bonds. So if one of the atoms is really, really, really electronegative and the other one's not, one is going to pull the electron off the other. It's a transfer of electrons. We call that an ionic bond. Electrons are transferred. That happens when the two atoms have a very big difference in electronegativity, bigger than 2. Polar bonds are sort of like that, but one doesn't pull the electron off of the other. It just sort of, the electrons tend to stay with it more than with the other one. So a 1.4 gives us a polar covalent bond, meaning the electrons spend more time here than they do here. And then a sort of a more pure covalent bond, like a nonpolar covalent bond, they're shared evenly. You're going to get a number less than 0.4. You don't have to memorize those numbers. I have them in a chart. That's not one of the things to memorize, but I do want you to know the difference between a nonpolar covalent bond and this one is called a polar covalent bond. The reason that it's called a polar covalent bond, you're still sharing, but it's an uneven sharing. So what does that look like? Well, these electrons, they're kind of spinning around both, and they're like, well, here's one proton. I'm kind of attracted to you, but I'm way more attracted to all these extra ones here. So they're going to go like, oh my God, I love you, I love you, I love you, I love you. I'll go around you a little bit. I love you, I love you, I love you, I love you. Oh, you're all right. So you've got 8 pluses, 8 protons, 9, 10. All together, you've got 10 protons. You've got 8 electrons, 9, 10. You've got 10 electrons. So notice that this is a neutral molecule. It's not an ion, right? It's a neutral molecule. Whoops, I missed a C, molecule. But the electrons, these shared electrons, spend more time here. So it's sort of like, over here you have 8 pluses, but more like 8.5 minuses. So it's sort of like you have a little bit, the electrons spend more time here than they do otherwise. I know there's more pluses, 8 pluses, right? But out of the 10 electrons, they're spending more of their time here. So if you have 8 protons and like 8.5 electrons, you're going to get a little bit of a negative charge. This sign right here means it's not a full whole charge. It's not like an entire proton or entire electron, right? It's not a full charge, but it's a partial charge. I might draw it like that, or I might draw it with parentheses around it. It means partial. Over here, these protons are left without electrons more often than not. Not always, but often. So that's got a partial positive charge. So water ends up being not only having polar bonds, but it ends up being a polar molecule. So what does that mean? A polar molecule happens when you have a sharing of electrons that's not even, so you have a polar covalent bond on a bent molecule. So let's say you have a molecule with some atom and then another one here and another one here. And well, let's see. Let me draw it like this. Let's say you have an atom like this and it's got one here and one here and one here. Let's say they're like this one's kind of behind and this one's in front. Um, they would sort of, if they're all equidistant from each other, maybe there's one in the back. Let's say it's got four and one's in the back. If they're all equidistant from each other, even if the bond between them is polar, you wouldn't have a polar molecule. But if you have this bent molecule like this, and one whole side of the one side of the molecule is more negative and one side's more positive, you get this thing called a polar molecule. That means you have an uneven charge distribution. So it's almost like an ion, but not quite. You have one side that's a little more negative here and one side that's a little more positive. So what do you think is going to happen when water mixes with anything? So that's what I want to look at next. So let's start by looking at what happens to salt, sodium chloride, when it dissolves in water, when it mixes with water. Well, what happens is you've got this positive ion here, the sodium, and so the negative side of water is attracted to it. And so you end up having water so attracted to it that it separates out the sodium from the chloride. So the sodium and the chloride used to sit right next to each other, right? But now you've got so many waters attracted to it that it sort of pushes the sodium and the chloride away. So I would want you to be able to draw the water with the positive parts, the hydrogen facing the chloride ion, and the negative oxygen side facing the sodium side. Those are called spheres of hydration or hydration shells. What you need to know is that ionic compounds dissociate in water. So ionic bonds are strong, but they break apart in water. So thankfully, you're made mainly out of covalent bonds. Otherwise, you'd be a puddle on the ground and you wouldn't be able to listen to this video, and it would be so sad, right? So there are important ionic bonds in your body. Proteins sometimes are held together in the right configuration um, with ionic bonds, but they also have a bunch of covalent bonds that are going to be holding them together too. Okay, covalent bonds are formed when atoms share two or more electrons. And so what you need to know with this is that it produces molecules. So they share electrons and you produce molecules. Here's a nice big covalently bonded molecule. It's a really big molecule. This one happens to be protein. I can see there's the nitrogen, carbon, carbon with an O, nitrogen, carbon, carbon with an O. I'll show you that soon, but here's a protein. The whole thing is all of these lines right here. Every line means a covalent bond. That's a double covalent bond right here. There might be ionic bonds in here somewhere, like maybe this one might form a positive charge and be attracted to, maybe there's a negative one somewhere. So ionic bonds can be important in shaping a protein, but most of the protein is made out of covalent bonding between atoms, and that's true for all of your molecules. Covalently bonded molecules do not dissociate in water. So this is showing you all those red and white little dots. That's a bunch of water that's surrounding these. So let me kind of back up and show you one other thing here. What you would see with covalent molecules, covalently bonded molecules like sugar, for example, carbon, oxygen, carbon. So what I'm drawing is kind of a lame picture of glucose. I'm not going to draw all the H's, but what they have is a bunch of hydroxyl groups, and I know I'm not, don't quote me on, like there's hydrogens, I'm not really drawing in the right direction, but we're going to live with that. Pretend I have 4 bonds coming off of every carbon. Anyway, see how this OH, that shape, the O to the H, doesn't that kind of look like water, right? Here's a water molecule. One side's negative, the other side's positive, right? This side's positive. This looks just like that, right? So how would sugar and water interact together? So sugar is a type of carbohydrate. It's a simple carbohydrate. I'm going to sort of draw this part like this, and then I'm going to draw some OHs hanging off. And so what I want you to think about, these hydroxyl groups here, what does water, oops, sorry, what does water do with that? So I didn't draw the carbons and everything, but good enough. So what would water do? Well, the hydrogen side of water is going to be attracted to the oxygen side, right? The positive to the negative. The oxygen side of water is going to be attracted to all these hydrogens. So water is going to surround the sugar. And so oxygen attracted to hydrogen. You would draw these as little dots. Don't draw a line. If you drew a solid line, it looks like a covalent bond. So I would want you to be able to label all of these as covalent bonds because it's actually a molecule. That O and the H are strongly connected to each other. Whereas maybe right here, I would want you to be able to label this as a hydrogen bond. That's a weak bond, but all of them together can really make a difference. Okay, so what you need to know is that covalent molecules, covalently bonded molecules, do not dissociate in water. And so that's good because now you're not a puddle on the ground. You're you. Yay.